All right. Problem 1. So this problem is saying in a long line of people arranged from left to right, the 1013th person from the left is also 1010th person from the right. How many people are on the line? So that one person is going to be this person right here. If they're the 1013th person from the left, that means there's 1012 people before them. If they're the 1010th person from the right, that means there was 1009 people before them. So now we can figure out how many people are in there. It's just 1012 plus the person themselves plus 1009, which is equal to 2022. Problem 2. What is 10 factorial minus 7 factorial times 6 factorial? Well, 10 factorial is equal to 10 times 9 times 8 times 7 factorial. This is equal to 720 times 7 factorial. But 720 is equal to 6 factorial. And this is just equal to 7 factorial times 6 factorial. So that means that our answer is just 7 factorial times 6 factorial minus 7 factorial times 6 factorial, which is 0. For this problem, we're asked to find how many integer values of x for which this is true. And this depends on finding out what 7 pi is equal to. So this is a little bit of a cursed problem because you got to know at least the first 3 digits of pi. You got to know this one right here. We know that 21 divided by 7 is equal to 3, which is less than pi. 22 divided by 7 is equal to 3.142. Oh, I should add some ellipses here. Is equal to 134 or 3.142857 repeating. And we'll notice that this 2 is the first digit that is different. The 2 is greater than the 1. So this is greater than pi. This first one means that 7 pi is greater than 21, but 7 pi is less than 22. So that means that absolute value of 2x has to be less than equal to 21, or 21, yeah, because if it equals 22, then it'll be more than 7 pi. So what this means is that that means that the absolute value of x can be anywhere from 0 to 10. Since x is an integer, we can just say it's less than or equal to 10. So x is going to be able to be negative 10, negative 9, all the way up to 9 and 10. And if we count how many numbers there are here, there's going to be 21 numbers. Problem 4. Balls numbered 1, 2, 3, and so on are deposited in 5 bins, which are A, B, C, D, and E. I'm going to scroll down a bit. And ball 1 is in A, ball 2 and 3 are in B, ball 3, 4, so the first ball is in A, the second, another 2 balls are in B, another 3 balls are in C, another 4 balls are in D, another 5 balls are in E, and then for the next 6 balls, we loop back to A and so on. So essentially all we're trying to do, and we're trying to find where ball 1, 2024 is deposited. So essentially all we're doing is we're counting up how many balls have been deposited with this expression. And we just want to find out when this is greater than 2024, when this first passes 2024, because while we're adding those number of balls, we're going to be depositing ball 2024. So the formula for this is one that is very helpful to know. It's equal to n times n plus 1 times over 2. So now we can just test values. Let's test, I don't know, n equals 50. This is going to be like, let's see, 25 times 51, which is 1250 plus 25 equals 1275, which is way too small. Let's try 60. This is probably going to be too small as well, but it's going to be closer. This is going to be 1830. So now this is when we add up to 60. So now if we add the next number, which is 61, that'll bring us to 1891. If we add the next number, which is 62, 1953. Now we can see that we're getting close. If we add the next number, which is 63, that brings us to 2016, which we're still not quite there yet. If we add the next number, which is 64, that brings us over. So that means that we got there during the ball 2024 was added during the 64th edition. And since 64 is congruent, since 64 has a remainder of 4 when divided by 5, that means that the 64th edition was in bin D, because like everything that is 1 mod 5 goes in bin A, 2 mod 5 goes in bin B, and so on. And because bin D gets the 4th, the 9th, and 14th, and so on, which includes the 64th. Problem 5. So we start with this expression, and we change some of the plus signs to minus signs, and it's negative. And we want to change as few plus signs to minus signs as possible. So obviously we want to change the plus signs on the biggest numbers so that we can subtract as much as possible. So that means that however much we're subtracting has to be more than however much we're adding for it to be negative. So essentially what we're going to have is we're going to have the first sum of these odd numbers be added, and then the rest are all going to be subtracted. So what does this initial sum equal? Well, this is the first 50 odd numbers, and it's helpful to know that the first n odd numbers add up to n squared. So this just equals 50 squared, or 2500. So that means that this sum needs to be greater than 1250, and this sum has to be less than 1250. Let me draw this for emphasis. We're adding all of these together, and this has to be more than this, which means that it has to be at least half of the whole sum. So now, once again, let's say this is the nth odd number, so it would be 2n minus 1. We would need the n squared is less than 1250. Well, and we want to make the biggest n as possible, because we want to have the biggest number of plus signs left. Well, the biggest n that satisfies this, we can just test, right? 35 squared equals 1225, but 36 squared equals 1296. So n is equal to 35. That means that we have 35 plus signs here, which means that since we have 50 numbers total, there are going to be 15 negatives, 15 minus signs. Problem 6. A rectangle has integer side lengths and an area of 2024. What is the least possible perimeter of a rectangle? So for this problem, when you have two numbers that multiply together, let's say the length and the width, they multiply together to be 2024. If we want to minimize the perimeter, which is essentially just adding these together, we want to make the length and the width as close together as possible. And it's helpful to know the factorization of the year, but 2024 is equal to 2025, which is 45 squared, minus 1. And this is just 44 times 46. So if we use these as the length and the width, we're going to get our minimum area. Or minimum perimeter, sorry. So our perimeter is 2 times the length plus the width, which is equal to 2 times 90, which is equal to 180. For this problem, problem 7, what is the remainder when this is divided by 19? For this problem, we might just start testing out small values of 7 to the n. So 7 to the 0 is equal to 1, is congruent to 1 mod 19. 7 to the 1 is congruent to 7 mod 19. 7 squared is congruent to 11 mod 19. But wait, what happens when we add just 7 to the 0, 7 to the 1, and 7 to the 2 up? 1 plus 7 plus 11 is equal to 19, which is congruent to 0. So 7 to the 0 plus 7 to the 1 plus 7 squared is divisible by 19. So that means that if we multiply the whole thing by 7 to the 2024, it's also going to be divisible by 0, or divisible by 19. But this is just equal to this. So that means the sum is divisible by 19. Problem 8. Let n be the product of all the positive integer divisors of 42. What is the unit digit of n? So what we want to do is we want to find how many divisors 42 has. Because for every divisor of 42, it has another divisor, which is 42 over d. And when we multiply these two together, it just equals 42. Essentially, the divisors come in pairs because 42 is not a perfect square. So 42 is equal to 2 times 3 times 7, 6 times 7. So this means that it has 2 times 2, no, 2 to the 1, 3 to the 1, 7 to the 1. So that means it has 2 times 2 times 2 divisors, which is equal to 8 divisors. So that means if we multiply all of the divisors together, there are going to be 4 pairs of divisors that multiply to 42. So our total product is going to be 42 to the 4. And if we want to find the units digit of this, that's the same as finding the units digit of 2 to the 4, which is just 6, because 2 to the 4 is equal to 16. Real numbers a, b, and c have arithmetic mean 0. So that just means that a plus b plus c equals 0. The arithmetic mean of a squared, b squared, and c squared is 10. So what that means is that a squared plus b squared plus c squared has to equal 30, because we divide by 3 to get to 10. What is the arithmetic mean of AB, AC, and BC? So we want to find AB plus BC plus AC divided by 3. So what we want to do is we want to square this first expression, because that'll give us a squares and ABs, BCs, and ACs. So if we square the first expression, or the first equation, we get a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ac equals 0. But now we see that a squared plus b squared plus c squared is equal to 30. So that means that 2 times ab plus bc plus ac has to equal negative 30. So now we can just divide both sides by 6. ab plus bc plus ac over 3 is equal to negative 5. And that's our answer. ABCD is a parallelogram, and E is a midpoint, and F is some intersection. So this problem, if you wanted to, you could try to prove that it's true for any parallelogram. But if you're on a time crunch in a contest, then you might just want to try fake solving it. It doesn't specify that ABCD has to be any old parallelogram. Let's just let ABCD be equal to a square. E is the midpoint of AD, and F is the intersection point of EB and AC. And now we want to find the ratio between this and this. So what we can see now, how do I want to do this? Okay, so what we can see now is that this angle is equal to this angle by vertical angles. And this angle is equal to this angle because they're both 45 degrees. And also because AD and BC are parallel. So that means that AFE is similar to CFB. What this means for us is that since E is the midpoint, AE and BC AE is exactly half of BC, so the scale factor is exactly 2. What this means is that EF is going to be half of FB, or EF, oops, and this also means that the area of triangle AEF is equal to half the triangle of AFB, because AEF and AFB are have the same height. So let's just let this triangle have area 1 and this triangle have area 2. Or no, this triangle have area 2. Oh wait, no. This triangle has area 2 and this triangle has area 4. Remember, because the scale factor from AFE to CFB is 2. So when we double the side lengths, we quadruple the area. And now we know that triangle ABC and triangle ADC have the same area since they're both half of the square. So that means that this quadrilateral here must have area 5 because we already have, because these two add up to 6 and these two have to add up to 6. So now we can see that the ratio is just 5 to 4. This problem is a bit of a mess. We have this big diagram. I'm not even going to bother to read the problem. I'm just going to label the numbers. So WX is 4, WZ is 8, this is a rectangle. This is a right angle, and these two have equal areas. And we're trying to find the area of this. So WZ is twice as long as WX. And if WZA and WXM have the same area, that means that XM has to be twice ZA. So let's just let ZA be X and XM be 2X then. Because now both of these triangles have area 4X. Then AY has to be equal to 4 minus X. And MY has to be 8 minus 2X. Now we can do 4 Pythagorean theorems. WM squared is equal to 4 squared plus 2x squared. MA squared is equal to 8 minus 2x squared plus 4 minus x squared. WA squared is equal to 8 squared plus x squared. And finally, WM squared plus MA squared is equal to WA squared. Oh, hey, Massachusetts, Washington. Hi, Maxwell. So now we can substitute each one of these into the big Pythagorean theorem. We have 4 squared. Okay, let's expand. So WM squared is going to be 16 plus 4x squared. MA squared is going to be 64 minus 32x plus 4x squared plus 16 minus 8x plus x squared is equal to WA squared, which is 64 plus x squared. So now let's collate all of the x squareds, x and constant terms on both sides. Let's cancel out the 64s to make things easier. And these x squared. And now we can see on the left side, on the left side, we have 8x squared, which are this 4x squared and the 4x squared, and then minus 40x, which is the minus 32x and minus 8x, and then plus 32 from the 16 and the 16 equals 0. Now we can just solve this quadratic. Divide both sides by 8. And x is going to equal 1 or 4. Clearly, x doesn't equal 4 because that definitely doesn't work. That would just mean that our triangle WMA just is a straight line here. So that means x has to equal 1. If x is 1, then AY is going to be... That means that we can now replace everything on this diagram. X is 1, 4 minus x is 3, 8 minus 2x is 6, 2x is 2. So now we can find WM and MA. WM is going to be 2 root 5, and MA is going to be 3 root 5. That's just by the Pythagorean theorem. So that means the area is 1/2 times 2 root 5 times 3 root 5, which is equal to 15. Ah, my hand. I'm going to drink some water. All right. Problem 12. We have 100 people, and they all speak the same number of languages. So let's say, and for every pair of students A and B, A speaks some language that B does not speak, and B speaks some language that A doesn't speak. What is the least possible total number of languages spoken by all the students? So let's say there's n total languages, right? And they all speak k of these languages. Then, essentially, all that we're saying is that no two students speak the exact same subset k of the n languages. So, for example, if a student speaks languages 1 and 2, and 3 and I don't know 5, then no other student has exactly these 4 languages. In this case, k would be 4. Let's say there might be another student with 1, 2, 4, and 5. Then there is a language that A speaks that B doesn't speak. That would be 3. And there's a language that B speaks that A doesn't speak. That would be 4. So since essentially what we're saying is that no student has a subset of the languages that another student speaks. And in our case, since every student speaks the same number of languages, that just means that no two students speak exactly the same languages. So in that case, all we need is to find an n such that we can have n choose k be greater than 100 or greater than equal to 100, because we need 100 different combinations of k languages out of the n for our statement to be true. And if we just try 9, that just straight up works, because 9 choose 4 is equal to 126, and we're done. Positive integers x and y satisfies root x plus root y equals root 1883. Let's factor that. 1183, I mean, not 1883. It's not divisible by 3. It's not divisible by 5. It's divisible by 7, I think. Let's try dividing by 7. It equals 7 times 1, 48. So we have a 6, 63. And then a 9. It's 7 times 1, 69, which is 7 times 13 squared. So root 1183 equals 13 root 7. Now, obviously, this means that x and y both have to have a factor of 7 in them. So let's say x equals 7a, y equals 7b. 7a squared, 7b squared. And then that means that we have a root 7 plus b root 7 equals 13 root 7. Since we want x plus y to be as small as possible, and we have a squared plus b squared equals, that's the same as making a squared plus b squared as small as possible, because x plus y is 7 times a squared plus b squared. And we're given that a plus b is equal to 13. So obviously, so what this essentially means, and in this case, since we're squaring them and adding together, we want to make a and b as close together as possible. So if a is 6 and b is 7, that's the closest together we're going to get. Since x and y have to be integers, this is going to be minimized. So once we do that, our final sum is just 7 times 6 squared plus 7 squared, which is equal to 7 times, let's see, 36 plus 49, 85, and this equals 595. A dartboard is the region where x plus y, the absolute value of x plus the absolute value of y, is less than equal to 8. So let's draw the coordinate plane. And the absolute value of x plus the absolute value of y is less than equal to 8. So let's just look at each of the 4 quadrants. In quadrant 1, x and y are both positive. So the graph is just x plus y equals 8, which looks like this. Oops. This. Where the intercepts are at 8. On here, it's on the second quadrant, x is negative and y is positive. So it's just negative x plus y is equal to 8, which looks like this. And so on. You get the idea. Essentially, we're just mirroring this line. We get a big diamond. A target T is the region where x squared plus y squared minus 25 squared is less than equal to 49. So what this means is that x squared plus y squared has to be within 7 of 25, because x squared plus y squared, okay, let me rephrase this. Minus 25, the absolute value of this has to be less than or equal to 7 if we take the square root of both sides, right? So that means that x squared plus y squared has to be within negative 18, or, oops, 25 minus 7, which is 18, to 25 plus 7, which is 32. We have to be between 18 and 32 for this to be true. But x squared plus y squared is just the distance of the point from the point to the origin. So that means that the target just looks like a ring, a donut, if you will. Moreover, the radius of the donut, the outer radius of the donut is 32, is square root of 32. And you'll notice that that means that it's tangent to this big diamond, because this point, which is 4, 4, is exactly square root of 32 units away from the origin. So let's draw the outer ring of this donut and the inner ring of this donut. What's the area of the donut? The area of the donut is just pi r squared of the outer ring minus the pi r squared of the inner ring. The area of the outer ring minus the area of the inner ring, which is 32 pi minus 18 pi, which is 14 pi. What's the area of the whole dartboard? Well, that's just going to be equal to these 4 right triangles added together. And the right triangles each have side lengths 8. And this is equal to 128. So that means our final chance is 14 pi divided by 128, which is equal to 7 pi over 64. And if we find m over n times pi, that's 7 over 64. We add them together, it's 71. Problem 15, which I think was probably the hardest problem on the test. A list of 9 real numbers consists of these 6 numbers, as well as x, y, and z, where x, y, and z are in that order. The range is 7. The mean and median are both positive integers. How many x, y, z are possible? So let's just write the numbers real quick. 1, 2.2, 3.2, 5.2, 6.2, and 7, as well as x, y, z. So the first thing we want to notice is that the range has to be 7. So either the smallest number needs to be 0, or the largest number needs to be 8, or we need to have some smallest number that is less than 1, and some largest number that is more than 1, that are exactly 7 apart. So essentially that means that all of our numbers are between 0 and 8, because otherwise the range would be too big. So let's first try to satisfy the condition of the mean. There has to be a positive integer. So let's add these numbers up right now. What does this equal? 3.2, 6.4, 11.6, 17.8. It equals 24.8. So that means that x plus y plus z is between 0 and 24. And we need this final sum to be a multiple of 9, because there are 9 numbers, so our mean has to be a multiple. So our sum has to be a multiple of 9 for the mean to be an integer. So that means we can go up to 27, 36, 45, or 54. Actually, we cannot go up to 54, because the maximum we can go up to is 48.8, since these 3 can only add up to 24. So these are our 3 possibilities. We have x plus y plus z equals 2.2, x plus y plus z equals 11.2, or x plus y plus z equals 20.2. Obviously, this first one is not possible. Okay, maybe that's not too easy to see. So we're actually not going to do casework based on this, but we're going to keep these in our back pocket. What we are going to do casework on is what we said earlier. Either the smallest one has to be a 0, the largest one has to be an 8, or we have to have the smallest and largest one have a difference of 7. So the smallest one equaling 0 would mean that the largest one has to be at most 7. This is going to be our first case. Our second case is where our largest one is equal to 8, and our smallest one is greater than 1, is at least 1, I mean. And the third case is where um, these are both have to be, whoops. These both have to be outside. I cannot write. So let's focus on this third case first. So what does this mean? If x is between 0, x still has to be greater than 0, remember. So x has to be between 0 and 1, and z has to be between 7 and 8. But y has to be an integer, because we need the median to be an integer. And neither the 7, nor the 1, nor x, nor z can become the median. That means y has to be the median, so y has to be an integer, which means that x and z in total have to add something 0.2, because y is not going to add any decimals. So the only ways are for x equals 0.1, z equals 7.1, or x equals 0.6, z equals 7.6. If x is 0.6 and z is 7.6, then that gets us to 8.2, which means y would have to be 3. But note that if y is 3, then it's not going to be the median. If we have 0.6 and 7.6. The median is going to be this 5.2, which is not going to be, or no, it's going to be this 3.2, which is not an integer. So that means that that's no good. This case is no good. If x is 0.1 and z is 7.1, we add up 7.2, which means y would equal 4. And this works. 4 would be the median, so this is so this is a valid case. This is working. Now let's go over to this case. X is 0, z is some number less than or equal to 7, and y is something. So now we can do casework. Let's have y and z add up to 2.2. This obviously isn't going to work because we need a number that's, since we're adding 0 to the set, this number or this number is going to become the median, which means that we need a number that's at least 4 to be the median. So then let's make it instead. Let's aim for 11.2. So we're going to do casework based on what the median is. If the median is 0, okay, the median can't be 0. The median has to be at least 4, as we said earlier. So, or no, the median has to be at least 3, because we could add a number before here. So let's start with the median being 3. If the median is 3, then we need 8.2. But this doesn't work. Z has to be less than or equal to 7. Same thing happens if the median is 4. Z is still too big. If the median is 5, then Z has to be 6.2. And this works. This satisfies all our conditions. If the median is 6, then it turns into the biggest number. And this becomes 5.2. But notice that if we add a 5.2 and we add a 6, then the median isn't the 6. The median is 5.2. So now we're dead. And if we keep going up, the median is always going to be the 3.2, or what the 4.2 here, and then a 3.2, and so on. And we're never going to get an integer median again, which means that this is our only solution for this case. Now we're going to go to the case where z is equal to 8. Once again, now we can do pretty much the exact same thing. For 8, we already cannot go for 2.2. We can try to go for 11.2, but that would require that, once again, but no, that's not allowed, because since we're adding an 8 and we can only add 2 numbers here, our median has to be at least 4. And we can, if we add 4, we're already up to 12. Let me drink some water, hold on. So that means that we have to aim for 20.2. So our other two numbers need to add up to 12.2. So now we can just try. Remember, our median has to be at least 4. So let's start with the median being 4. And then our other number is 8.2, right? That doesn't work. This is not, our biggest number is 8. It doesn't work. If the median is 5, 7.2, then if we try inserting these numbers, we can see that our median is going to be this 5.2. It's not going to work. If our median is 6, and we have a 6.2, then this works. 6 is the median. If our integer is 7, then it's never going to be the median again, because it's only going to get bigger and bigger. We're going to add a 5.2 here, and then the median is always going to be a 5.2, and it's never going to be an integer again. So now we're done with all our test cases. How many solutions are there? 1, 2, 3. The answer is 3. This problem really sucks, and it's probably the hardest problem on the test. All right, on to the next one. So we have all the numbers 1, 2, all the way to 2024. And then at every step, we can choose 4 numbers and then either add them and multiply them. So that means that we took in 4 numbers and we outputted 1 number, which means we always subtract 3 numbers at every step. So that means that if we divide by 3, our remainder never changes. We're always, in other words, it's the number of integers is invariant mod 3. So that means however many numbers we have left at the end, it has to be the same mod 3 as 2024, which is congruent to 2 mod 3. No, it's not. Yes, it is. It's 2 mod 3. So that narrows it down to 1020, 1013, and 1010. Now, our second observation. The number of odd numbers will never increase. Think about it. We take in 4 numbers, and we output one number. If the number of odd numbers increases, the only way we can do that is to take in 4 even numbers and output 1 odd number, because we would delete 0 odd numbers and add 1 odd number. If there were any odd numbers on this side, then we would never get an increase in the number of odd numbers, because we would, in this case, if there was 1 odd number, then we would take in 1 odd number, we would get rid of 1 odd number and add 1 odd number, which does not increase. That keeps the same. If there's 2 odd numbers here, that doesn't increase either, and so on. The only way we can increase the number of odd numbers is by taking in 4 evens and outputting 1 odd number. But if we add 4 even numbers, it's going to be even. If we multiply 4 even numbers, it's going to be even. So this is impossible. That means that the number of odd numbers can never increase. And since at the end we have that all of the numbers at the end are odd, which means that the most number of numbers at the end has to be 1012, because there's only 1012 odd numbers to begin with, and we can't increase the number of odd numbers, which means that 10,000 or 1013 is not possible, and the biggest possible number is 1010. And there is a way to do this. Essentially what you do is you take all of the even numbers and you keep on killing off all of the even numbers by adding or multiplying together until at the end you're left with 1 even number, I think. You're left with 1 even number, and then you add it with 3 odd numbers, and you're left with 1010 odd numbers. That's a way you could get to 1010 odd numbers. Problem 17. In a race among 5 snails, there's at most 1 tie, but that tie can involve any number of snails. How many different results are possible? So we have A, B, C, D, E, right? So let's have cases. If there's no tie, then it's easy. It's just 5 factorial is 120 ways. If there's a tie, if there's a tie between 2 snails, exactly, then there's 5 choose 2 ways to choose the 2 snails that are tied, and then there's 4 factorial ways to arrange those 2 snails and then the 3 other snails, because we can treat the 2 snails as a singular position, and then we're just ordering the 3 snails and those 2 snails together. So there's 4 factorial ways to do that. If there's 3 snails tied, then we can do the same thing. 5 choose 3 ways to choose the 3 snails tied times 3 factorial ways to order them. If there's 4 snails tied, there's 5 choose 4 ways to choose the 4 snails tied, and then 2 factorial ways to order. And then if all 5 snails are tied, then there's only 1 way. All of them are tied. All of them are first. So if we calculate these, we can find 5 choose 2 is 10. This is 240. 5 choose 3 is 10. This is 60. 5 choose 4 is 5. This is 10. And this is 1. And now if we add all of these up, 120 plus 240, 360, plus 60 is 420, plus 10 is 430, plus 1 is 431. Problem 18. How many different remainders can we have if we have how many? Okay, so this is just asking if we take n to the 100 mod 125, what can we get? So note that if n is multiple of 5, it's always going to be 0. If n is not a multiple of 5, then there's this nifty little thing called Fermat's little theorem, which says that since n is not a multiple of 5, it's going to be relatively prime to 125. So that means we can apply, oops, where is it? Shoot. Okay, so that means, hold on, I need to get back there. I'm a little dumb. That means we can apply Euler's totient function, or Fermat's little theorem, which says that n times the totient of 125 is always going to be congruent to 1 mod 125. And totient of 125 is equal, that's the number, by the way, that's the number of numbers below 120 and 5 that are relatively prime. That's just going to be every number that is not a multiple of 5. And that turns out to be 100. So that means that if n is not a multiple of 5, then n to the 100 is always congruent to 1 mod 125. So that means that our only options are 0 and 1, which means there are 2 different remainders. Problem 19 is literally an algebra 2 problem. It's a little annoying. We're asking, this is the number of lattice points that the line passes through, and this is the slope of the line. So, a 0 slope line can obviously pass through 0 lattice points. This is definitely possible. We just say like y equals 0.5 or something. That'll never pass through a lattice point. It can't pass through one lattice point exactly, because if it passes through one lattice point, then it's going to pass through a million others. Same thing with 2. It's always going to pass through other lattice points. And it can obviously pass through more than 2. Let's just say y equals 1. That passes through like infinitely many lattice points. A non-zero rational slope can also pass through 0 lattice points. Consider y equals x plus a half. Y and x can never both be integers. An integer is never going to be a half more than another integer. We can never pass through exactly one lattice point, because a non-zero rational slope means the slope has to be some a over b. But that means that if x and y are integers and we increase x by b and we increase y by a, then that's still going to be on the line. So we're always going to be passing through infinitely many lattice points if we pass through any at all. So it can't be 2 either for the same reasoning, and more than 2 are definitely possible using the same one. For an irrational slope, I'm not sure why I dotted these in. These should be circled. For an irrational slope, it's definitely possible to pass through 0. Just say like y equals pi x plus e or something. You're never going to pass through a lattice point. It's also possible to pass through exactly 1. Because we can just have y equals pi x or something. That's never going to be passed through any lattice point other than 0, 0. However, if we pass through exactly 2 lattice points, then the slope is not going to be rational, because if we pass through, say, this lattice point and this lattice point, then the slope is just going to be this distance divided by this distance, which are both integers, which would make it rational. But the slope is irrational, so it means we can't pass through 2 or even more than 2, because we could just choose any 2 points. We can't pass through more than 2 lattice points with an irrational slope either, because otherwise the slope would be rational. If we count up how many we have, there's 6. Why did I circle it? Okay. Problem 20. We have 3 pairs of shoes. Let's say they're left 1, right 1, left 2, right 2, and left 3, right 3. No left shoe is next to a right shoe from a different pair. That means that every right shoe That means that a right shoe. Okay, essentially what that means is that a right shoe cannot have two left shoes next to it, because one of these is going to have to be a left shoe from another pair, and that would violate it. That would violate the condition. So what we're going to do is we're going to place the right shoes first. So, keeping in mind that no right shoe can have two left shoes next to it, that means that every right shoe has to either be next to another right shoe, or it has to be on the edge. So, if a right shoe, so we're going to not worry about which right shoe is which for now, because at the end we can always reorder 1, 2, and 3. We can always multiply by 3 factorial. And we're also going to only consider non-reflected things to make it easier on ourselves. We're also going to consider reflections as the same. This is not going to be allowed. This is not going to be allowed, but this is allowed, because the right is on the edge and it's only next to one spot. Now, let's consider the cases. Okay, hold on. Let me redo this. So, first things first, we're going to consider the cases where all 3 rights are together in a cluster. That means that every right is next to another right, which will always work. These are the only 2 cases, because note that this is just the same as this, but reflected. So now we're going to consider the case where there's one right shoe on an edge, and then the other 2 right shoes are somewhere in the middle. We don't have to worry about the right shoe being on the other edge, because we're not considering reflections. We consider reflections by doubling it right here. So these are all of our cases. So now let's just label each one of these 1, 2, and 3 in some order, because we can always change the order of 1, 2, and 3 later. The 1, 2, and 3 order was determined by this, by the way. We're multiplying by 3, so we don't have to worry about that. 3 factorial, I mean. So here, this spot has to be a left 3, because no other shoe can be next to right 3. But now, for these 2, they can be in any order. So that means we have 2 ways to do this one. This shoe has to be left 1. This shoe has to be left 3 because it's next to right 3. And that means that left 2 has to be here. This shoe cannot be anything, because if it's left 1, then it's next to right 2. But if it's left 2, then it's next to right 1. So that means that this is just impossible. This shoe has to be left 1. This shoe has to be left 2. And this shoe has to be left 3. So that's one way. This shoe has to be left 1. This shoe has to be left 2. And that leaves this shoe has to be left 3. So that's one way. Finally, adding all of these up, we can see that we have 5 ways. But we have to consider all of the symmetry that we did before. 2 times 6 times 5 is equal to 12 times 5 equals 60. So our answer is 60. Oh god, this problem. Oh my god. Okay. So what we have is that the radii of these are 1 and 1/4. And we have a third circle that is also going to be tangent to everything. And we're trying to find the possible radii. So there's 2 possible radii. One case is that the circle is here, and the other case is that the circle is here. Okay? So, what we're going to do is, let's do the big case first. So, an interesting thing of note is that since this is 1/4, we have that this is 3/4. And since this is 1/4 and this is 1, this is 5/4. And if you notice something interesting, this is 1. So that means that this is symmetric because this is 1 and it intersects. If this is 1, then it's directly over this because we have 1 here and 1 here. So that means that by symmetry, the radius of this other circle is also going to be 1. So the radius of the big circle is 1. That's just a neat coincidence that we have. You could do it with the same method that we're doing for the smaller circle, but it's really annoying. So that means one of the bigger radius is equal to 1. So let's find the smaller radius. And we're going to do that by drawing this line right here, and this line right here, and this line right here, and this line right here. And essentially what we have is that these two lines need to add up to 1. So the length of this line right here is equal, let's let the radius of the small one be r, okay? So then by the Pythagorean theorem, we have that 1 plus r, which is this length from the center of this circle to the center of the small circle, from the center of this circle to the center of the small circle, squared minus this is from here to here is going to be 1 minus r. The square root of that plus, we can do the same thing for the smaller circle. It's going to be 1/4 plus r, 1/4 minus r. This has to equal 1 because we found that this was what the whole thing was 1 earlier. So now we can just use some difference of squares to make this calculation easier. This is going to be square root of 4r plus the square root of r is equal to 1. Or 3 root r equals 1. So that means r is 1/9. The small radius is equal to 1/9. So our sum is 1/9 plus 1, which we found earlier right here, for a total of 10/9. I believe the theorem for this is called like Descartes' circle theorem, but I never bothered to learn it, so you can always derive it. It takes a bit of time though. Problem 22. A group of 16 people is partitioned into 4 indistinguishable 4-person committees, and we're choosing a chairperson and a secretary for each one of these, and we're trying to find how many ways there are to do that. So the first thing we're going to do is to choose these committees. So let's just choose one committee. There's 16, choose 4 ways to do that. And then let's choose a second committee. There's 12, choose 4 ways to do that. Let's choose a third committee, which is 8, choose 4 ways, because we already used up the other people. And the last committee has 4, choose 4 ways. Because there's 12 here because we already used up 4 people for the first committee. 8 here because we already used up 4 people and 4 people for the first 2 communities, and so on. But now we have to divide by 4 factorial, because we could have chosen these committees in any order. And now we need to choose a chairperson and a secretary for each committee. There's 4 ways to choose the chairperson in a committee, and there's 3 ways to choose the secretary, because we've already chosen the chairperson. And I assume the chairperson and the secretary can't be the same person. I think that's a bit of a problem with the problem, actually. They should have specified that the secretary and chairperson can't be the same person. Anyway, but I digress. And we have to do this for each committee, so 4 times. And we're trying to find the number of factors of 3 in here. Well, if you'll notice, this is equal to 16 factorial divided by 4 factorial to the 5th power multiplied by 4 to the 4 times 3 to the 4. In 16 factorial has how many powers of 3? There's 15, there's 12, there's 9, which contributes twice, there's 6, and there's 3, which means there's 6 factors of 3. 4 factorial has 1 factor of 3, but since it's to the 5th power, we have to have 5 powers of 3. And since it's divided, we have to have -5. And then 3 to the 4 is just 4 powers of 3. So once we add all of this together, we get that the total number of factors of 3 is 5. Problem 23. Oh no. Okay. Problem 23. Fn is the nth Fibonacci number, and we're trying to find this sum. This problem is a great example of engineer's induction if you don't want to prove things. So let's just list out the Fibonacci sequence real quick. So we have what? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. That should be enough. So the first one, f2 over f1, is equal to 1. 1 over 1. f4 over f2 is equal to 3. That's 3 over 1. f6 over f3 is equal to 4. That's 8 over 2. And then f8 over f4 is equal to 7. That's 21 over 3. f10 over f5 is equal to 11. That's 55 over 5. f12 over f6 is equal to 18. That's 144 over 8. And now you might be seeing a pattern. We have another Fibonacci sequence. 1 and 3 add up to 4. 3 and 4 add up to 7. 4 and 7 add up to 11. 7 and 11 add up to 18. And these are actually what are known as the Lucas numbers. It's essentially just like the Fibonacci sequence, but you start with 1 and 3. And they occur when you divide this kind of like doubling divide Fibonacci number f of 2, the 2n and n Fibonacci number. But you don't really need to prove that in a short answer contest like this. All you need to do is just observe this this pattern. We can use engineer's induction to just assume that this goes on forever, and it indeed does. And we just want to find the first 10 of these, because it goes on up to f20 over f10. So we get 29 is the 7th one, and then 47 is the 8th one, and then 76 is the 9th one, and then 123 is the 10th one. So now let's just add these up. We get 4, we get 8, we get 15, we get 26, we get 44, we get 73, we get 120, 196, 319. Our total sum is 319. Problem 24. We're finding how many of these are integers. So the first thing to note is that obviously the even numbers always work, because this is going to be an integer, this is going to be an integer, this is going to be an integer, and this is going to be an integer, because this is going to have at least 16, this is going to have at least 4, this is going to have at least like 256, and this is always going to be an integer since m is even. So these two already work. Now we want to consider the odd ones. So the odd ones for m over 2, it's always going to be some integer plus a half. For m squared over 4, we can note that if m is congruent to 1 mod 4, and if m is congruent to 3 mod 4, which are the two possibilities, mod 4 for odd numbers, then m squared is always going to be 1 mod 4. So that means that m squared over 4 is always going to be an integer plus a fourth, because m squared is always 1 more than a multiple of 4 for if m is an odd number. And now let's do the same thing for 8. The two odd numbers we're considering are 2023 and 2025, sorry. But 2024 is divisible by 8. So 2023 is congruent to -1 mod 8, and 2025 is congruent to 1 mod 8. But you'll note that -1 to the 4th power and 1 to the 4th power, they're all just 1 mod 8. And the same thing with the 8th power. -1 to the 8th power is the same as 1 to the 8th power, which is also 1 mod 8. So that means that m to the 4th, and m to the 8th are also both going to be 1 over a multiple of 8. If m to the 4th power and m to the 8th power are both 1 over a multiple of 8, then this sum is 2 over a multiple of 8, which is going to be equal to an integer plus a fourth. And now you note that if we add everything together, these three integers add up to an integer, and 1/2, 1/4, and 1/4 add up to 1, which means that it's also an integer for both 2023 and 2025. So it works for all of them, so our answer is 4. Problem 2025, or problem 20, problem 25 is Surprisingly easy for a problem 25. We have A, B, and C, and we have this 3 by 3 by 3 here. And then we again have A, B, and C, and then it's a 2 by 2 by 7. And it says that it's 1 unit larger in each one dimension. So let's just look at the length here. The length on the old one is going to be 3C. This dimension on the old one is 3C. This dimension on the new one is 7A, and it's 1 more than 3C. This dimension on the old one is 3A. This dimension on the new one is 2B, and it's 1 more than 3A. This dimension on the old one is 3B. This dimension on the new one is 2C, and it's 1 more. So now we can just solve the system of equations. You can do this however you like. I did this the pretty caveman way. I just took the first one into C is equal to 7A minus 1 over 3, and then plugged this into the third one. So 3B plus 1 is equal to 14A minus 2 over 3. So this means that P is equal to 14A minus 5 divided by 9. And now we can plug this into the second one. 3A plus 1 equals 28A minus 10 over 9. So multiply both sides by 9. 27A plus 19 equals 28A. So that means A has to equal 19. And then B has to equal 14 times 19 minus 5, which is going to be 261 minus 5 over 9, which is 250, what? 255 over 9? What's 255 over 9? That's going to be, wait, that's not divisible. Did I do something wrong? Hold on, I can't find the mistake. Hold on. C is 7A minus 1 over 3. 3B plus 1 is 2C. 14 times 19 is 261. Let me just confirm that. 14 times 19. How can... Oh my gosh. I'm so sorry. 14 times 19 is 266. Minus 5 is 261. And then when we divide by 9, it's going to be 266, or 261 over 9, which is going to equal 29. And then finally, C is going to be 7A minus 1 over 3, which is going to be 7A is equal to 143, 133. Minus 1 is 132, over 3 is 44. And now, this is our, we're not just finding oh, okay, it just asks us to find A plus B plus C. All right. A plus B plus C is just going to be the sum of these, which is 92. And that's it.